All right, it's like 9:30 and stuff, and we got crap to do today, so let's go ahead and get started. Can the people on Zoom hear me? I just want to make sure because I'm not hearing anything out of my computer whatsoever, even though the volume is turned all the way up. Yes, okay, great. All right, so when we left off on Monday, we had looked at our feedback network and figured out how to determine our loading resistances R11, R22, and our feedback factor K. So now we have enough information to construct our open loop gain circuit. Okay, so our open loop gain circuit is going to look something like this. Sorry, took me a moment to get back to that place in my notes. So we're going to have our generic open loop gain circuit from our original model. But now it's going to be modified with those parameters. So we're going to have RS. Here we will place R11 on this side. We will have R22. And our load resistance. And then we can define our open loop gain. A1 will be, by definition, V out divided by our applied voltage VI. We can also use this circuit to determine our open loop input resistance, which I've labeled here as RI, and our open loop output resistance, which I've labeled as R naught. So we now have a means by which to calculate K, our feedback factor, and A1, our open loop gain. So we have everything that we need to be able to put into an equation to simply solve for our gain with feedback AF. So from here, we have AF is equal to A1 over, 1 plus KA1. Our IF, our input resistance with feedback, is going to be RI, our open loop input resistance, times a factor of 1 plus KA1. And then our input resistance of our system, and just to be clear here, let's look back at our original diagram. Our input resistance is just going to be, here we can see that we have RIF in series with RS. Looking in from here, we are excluding the source resistance RS. That's all we're doing. So we'll have RIF minus RS. Then our output resistance with feedback ROF is our open loop output resistance divided by our amount of feedback. And similarly, we can say that R out, which is just our output resistance not including the load, is going to be 1 over ROF minus 1 over RL to the -1 power. So it's getting rid of that parallel load resistance. Pardon?
Like in the RO equation, you have it's RO in the numerator. So will we see that or R out subscripts?
I don't understand your question. Yeah, RO is the open loop gain or open loop output resistance. R out is a closed loop output resistance that does not include the load quantity. So they represent two different things. Okay. All right. So as some of you have mentioned prior to class, there's been a little bit of a disconnect between what we are doing right now and then your ability to say complete your homework assignment and things like that. So with that in mind, I have prepared several examples. And so that's what we're going to spend the rest of today's class period doing. All right. Let's see. So let's look at a first example problem. Wherein we have the following transistor amplifier. So here's R1. Here is R2. We are going to, in this particular example, assume that R1 and R2 are much, much greater than RD. And our goal is to determine our gain with feedback or our closed loop gain AF, our closed loop input resistance RIF, and our closed loop output resistance ROF. So I guess the first thing that I want to ask is, do you guys see why this is a amplifier with feedback? Well, let's start with something real simple, okay? So there's the resistor R1 is connected from the output to the gate. So it's not directly tied from the output to one of the input signals like we saw with our op amps. But the purpose of the feedback network isn't to connect directly to the input. It is to add or subtract a voltage from the input signal, right? So if we have this resistor connected between the output and the gate, that means that the gate source voltage of that transistor is going to change depending on what the output signal is. And so therefore we have feedback in place. It is going to be negative feedback because we will see that as our output resistance increases, the voltage at the gate increases, which is going to make our gate source voltage smaller, or so if this guy goes up, the feedback makes it go down. So we have negative feedback in place. All right. Under the assumption that R1 and R2 is much greater than RD, effectively what this means is that we are saying we do not believe that our feedback network is loading the input or the output network of our open loop amplifier. So effectively, we treat this guy as an open loop circuit with no feedback, and we can get our different parameters from there. We will immediately after this example work the problem and assume that we do have loading effects and see how to treat it in that way. And we'll find out that if we do the math, they are effectively the same thing when the values of R1 and R2 are very large in comparison to RD. Like I did a MathCAD sheet to literally prove that. So we could actually work all problems under the assumption that our feedback network does load the system and still get the correct answer. All right, so with that in mind, how could we go about determining the open loop gain of this system under the assumption that the feedback network isn't loading anything? Any thoughts? So if I didn't have R1 and R2 and I just applied some fixed bias voltage at my gate, what kind of amplifier would this be? My input is being applied at my source. My output is being taken at my drain. Common gate, okay? Common gate amplifier has a gain of what? Yep, GMRD. So that is our open loop gain. It is that simple. So our open loop gain, A1, is GMRD. Again, when we have assumed that our output, or excuse me, our feedback network isn't loading anything. To find our feedback factor, we're going to have to look at our feedback network. So remember, for our feedback network, we have a simple two-port network where port 1 is where it's connected to the input, port 2 is where it's connected to the output, right? So I can see that between my output and my input or gate here, I have a resistor R1. And connected at the input side, I have a resistor R2 between port 1 and ground. So this is the configuration of my feedback network as compared to those two port locations. So based on this, what should my feedback factor be? Remember, we would get our feedback factor by, say, applying some test voltage, which I'm just going to call V out, measuring my feedback voltage VF, and my feedback factor by definition will be VF over V out. So what's it going to be? This is a circuits 1 question at this point. Yeah, R2 over R1 plus R2. While we are at it, what is our open loop input resistance going to be? So that would be us looking in here, where again, we are assuming that we are not loading the input terminal in any way. So what do we get when we look through the source of a MOSFET? That's correct. 1 over GM. That's it. If we look in through the output, again, ignoring the effects of the feedback network, what do we see? RD. So from this, our closed loop gain, which is just A1 over 1 plus KA1 is going to be GM RD over 1 plus R2 over R1 plus R2 times GM RD. Our input resistance, RIF, is going to be 1 over GM times 1 plus KA1. So 1 plus R2 over R1 plus R2 times GM RD. And our output resistance with feedback R naught F is going to be RD over 1 plus KA1. So that'll be 1 plus R2 over R1 plus R2 times GM RD. So we have successfully completed homework 5, problem 3. That is this problem. Was this difficult? Not particularly. All right. So let's make things slightly more difficult by including loading effects. Okay. So we're going to do the exact same problem. But now we're going to assume that R1 and R2 are of roughly the same magnitude as RD. Process is going to be slightly different, but it's only slightly. Here's R1, here is R2. We are going to assume that R1 and R are approximately RD, somewhere in the ballpark. And we want to find our gain with feedback, our input resistance with feedback, and our output resistance with feedback. So the exact same quantities, okay? So since we are making the assumption here that R1 and R2 are approximately the value of RD, we now need to look at our feedback network first, because that's going to tell us our feedback factor, which shouldn't have changed at all, but it's also going to give us our loading resistances R1 and R2, which are used to form the open loop circuit so that we can tell what our open loop gain is when our system is loaded, okay? So as we saw a minute ago, our feedback network is this guy right here. Here's port 1 with this guy is R2. Here is port 2. R11 we find by looking into 1 with 2 shorted. So what will that value be? So if we short circuit port 2 and look into port 1, what do we see? Those two in parallel, right? So R1 in parallel with R2. R22, we see by looking into 2 with port 1 open. So what is that going to look like, Evan? They're in series. Yeah, so R1 plus R2. Our feedback factor K, again, we would find it the exact same way we did in the last example problem. It cannot have changed because it is literally the exact same feedback network. So it's just going to have a value of R2 over R1 plus R2. So from here, we can now construct our open loop circuit. So we're effectively breaking the feedback loop and then loading the parts as is correct, okay? So I'm going to redraw my circuit. Here's VDD. Here is RD. Here is V out. Here is V in. All right, so now let's talk about how we place R11 and R22. So R22 is the resistance that we see looking into port 2, which was the port connected to our output. So we simply place R22 between our output and ground. R11 is the resistance we saw connected to the input. So we're going to place it between the input or the gate and ground. This is our open loop circuit, by which we can determine our open loop gain. So by inspection, what is our open loop gain for this system? Right, so GM multiplied by RD in parallel with R22. Anybody have any problem with that? Hopefully fairly straightforward, right? Why is R11 at the gate and not the input at the source? So our feedback network wasn't connected directly to the source. It was connected to the gate. So this is different than if we were looking at an op amp where the feedback is tied directly to that input terminal. We are considering the feedback to just be some mechanism that will allow us to add or subtract a voltage to our input voltage, right? So the current through this thing is controlled by the gate source voltage, VGS. Vin is Vs. The other part of that is Vg. So Vg is what we're considering our input terminal for this guy, because that's where we're applying the feedback signal. Exactly right. Another way to put it, Mr. Greer said, it's the port input, not the system input, which is a perfectly great way to look at it. So that's why we're connecting it to the gate. So if we were to look in, what would we see? 1 over GM again, right? So loading didn't change our input resistance. What do we see when we look in through the output terminal now? RD in parallel with R22. So from this, our gain with feedback, AF, just to be clear, it's A1 over 1 plus K A1 is going to look like GM RD in parallel with R22 divided by 1 plus R2 over R1 plus R2 GM RD in parallel with R22. Our input resistance with feedback is just 1 over GM times 1 plus KA1. And our output resistance with feedback will be RO, which is RD in parallel with R22, divided by 1 plus KA1. All right, so give me just a moment to pull up MathCAD. Oh, what the heck is going on there? All right, a while that. Power cable was bending it at a slight angle. Let's open up some stuff. Let's see, Dropbox 336. I can't see. I feel like that's the first one. All right, so I did it slightly backwards. Let me get my mouse up so this is going to work. So assuming the feedback network loads the bias amplifier, so this is technically our work for problem 2. We can see that with, these are the parameters that I was given when I look at the web work problem or whatever. So R1 is 29K, R2 is 71K, RD is 200 ohms. R1 and R2 are much, much greater than RD, so it's probably safe to assume that they don't load things. But if we work the problem this way, these are the answers that I get. We get a voltage gain with feedback of 1.298, which is equivalent to 2.269 decibels, an input resistance with feedback of 153.7 ohms, and an output resistance with feedback of 15.582 ohms. If we work the problem where it doesn't load anything, we can see that our numbers are almost identical. So I would argue that to be on the safe side, because in some circuits it's not going to be obvious as to what resistance we need to be comparing things to, it might be in your best interest to work all of them as if the feedback network is loading the output and input ports. It really doesn't require a whole heck of a lot more math and all that kind of good stuff. And you're always going to be very, very close to the correct answer. Okay, so yeah.
I mean, that's the truth.
Yes. Yeah, we're making no assumptions here. We are including them. So I would concur with that statement. All right. Any questions regarding this problem where we have a simple single stage amplifier with feedback? Evan, what's up?
So would the MOSFET be the mixer or the open?
Both. It is both the feed forward network and it is also responsible for mixing the signal. Because the current flowing through this guy, which is what the output voltage is dependent on VGS, where VGS is the mixing of our true input signal and our feedback signal.
They don't have to be.
Yeah, they do not in any way, shape, or form have to be two separate things. Yeah.
But they actually usually come out to be the same thing. Like, are most systems one device is over?
It really depends on the configuration and all that kind of stuff. So like there's a problem that I'm going to work on Friday with a laser diode where the measure resistor is both the feedback network and the output sensing portion, but it has nothing to do with the mixing. So it just depends on the system. Yeah. We can't say easily, it's going to be this. It literally just depends on what we're looking at. All right. So any other questions with regards to this problem? All right. Let's increase our level of difficulty slightly. All right. Okay, let's say that I have the following circuit. Call this guy RD1. Call this guy up here RD2. Here is R1. Here is R2. Here is where we take our output signal. Let's call this transistor M1 and this transistor M2. So we now have a multi-stage amplifier circuit, right? Effectively what we have is a common source stage feeding a second common source stage with feedback cleaning things up, all right? So our feedback network, in this case, oops, not what I wanted to do, close that. Here's port 2, here's port 1. What kind of connections should I have? So R1 is going to connect port 2 to port 1 because it's connected between the output and the input. And then R2 is placed between the input and ground. So the exact same feedback network as we had before. Just for the sake of argument, if I only had a feedback resistor here with no connection to ground, we would just have that resistor R1. If I shorted this guy, we would just have the one between the top node and the bottom node. So we can definitely, like in the textbook, there's a couple of examples where the feedback network is literally a wire. So that's also valid, but we're used to seeing things with resistors. So for now, I'm going to be working stuff with resistors. So what is my loading resistance R11 going to be? Again, that is looking into port 1 with 2 short circuited. They're still in parallel. Yeah, it's the exact same feedback network as we had before. So we have R11 is R1 in parallel with R2. R22, they're still in series. So that's R1 plus R2. And then our feedback factor K is just R2 over R1 plus R2. Okay. So now we have everything that we could possibly need to construct our open loop circuit to determine our open loop gain. So let's draw that guy. So I'm going to connect R11, the input port loading resistance, to the input, which in this case would be the source of transistor M1. So this is where R11 goes. I'm going to connect my loading resistance R22 to the output, which is the drain of transistor M2. And this is my open loop circuit. Everybody okay with where I've placed my loading resistances based on the mechanisms that we've established? All right. So by direct inspection, I would argue that the open loop gain of this circuit is maybe a little bit harder to do. So to make our life slightly easier, I'm going to label this node as X. Our open loop gain, A1, is going to be Vx divided by Vn multiplied by Vout over Vx. So I'm simply just breaking this guy up into two discrete stages. What is, let me put a dashed line through this guy. So everything to the left is the first stage, which has the transfer function of Vx over Vn. Everything to the right of the dashed line is the second stage, which has a transfer function of Vout over Vx. So what does our first stage, or our left stage, look like? Yeah, common source amplifier with source to generation, which has a well-defined gain that we hopefully don't need to derive again at this point. So I'm just going to go ahead and say that it's negative GM1 times RD1 divided by 1 plus GM1 R11. This is literally one of the amplifiers on the back cover of your textbook that it tells you what it is. So that's a common one. What about our second stage? We have V out over Vn. So what does our second stage look like? So we're just applying some voltage X at our gate, some small signal voltage Vx at the gate of transistor M2, and it's amplifying that signal in some way, shape, or form. What is it doing? What is it? Sorry, I meant V out over Vx. Thank you. Let's see what's popping off in chat here. Okay, yes, Nathan also noticed that. All right, so what is V out over Vx? What is the transfer function for my second stage? What kind of amplifier is it? Common source with some loading resistance. Yeah. So what's it going to be? Evan, you were going to say something. Right, so negative GM2 times RD2 in parallel with R22. And so our open loop gain is just the product of these two guys. So that's going to be GM1, GM2, RD1 times RD2 in parallel with R22, all divided by 1 plus GM1 R11. What is our open loop input resistance? Yeah, it's infinitely large because it's just running into the open circuit of the gate source capacitance. Sorry, not R out, R not. What is the open loop output resistance? That's it. RD2 in parallel with R22. And now we have a means by which we could go ahead and calculate the closed loop gain, the input resistance with feedback, and the output resistance with feedback. Once we get the gain circuit and determine the open loop gain, the input resistance, and the output resistance, we're done analyzing the circuit, right? At this point, it's just throwing crap into an equation and seeing what falls out. So do I need to actually go through those steps? All right, so this one was a little bit more difficult. Let's just really mess with you guys now. This will be our last example. So this problem would be something way more difficult than I could ever ask you on a test. So if this makes sense to you, you're doing very, very good, okay? That's two. Let's call this guy M1, this guy M2. So this guy will be IS12 here. Oh, sorry. Call this guy IS3. This is transistor M3. Here's our load resistance. Here's where we are taking our output. So what this guy looks similar to, but is not exactly, would be a differential pair being used to supply the input voltage to a common, to a source follower, right? It looks like that, but it isn't exactly that because our differential pair isn't exactly a differential pair. Why is it not exactly a differential pair? It's not symmetrical, right? Because it's not symmetrical, we can't say, oh, we can't look at the half circuit and just break that stage down by looking at a half circuit and calling it a day. We're going to have to actually go through the steps of analyzing, okay? Our feedback network is, again, just that resistor R1 placed between the output and then what would be considered the inverting input of the differential pair. And then we have a resistor R2 between that input and ground. So we have, again, the exact same feedback network that we have had before. So just for the sake of argument. Oh, okay. Thank you. Is the resistor furthest to the right also R2? No, it is RL. So there is a load resistor connected between the output and ground. The feedback resistors are R1 and R2, and there is a resistor RD connected to the drain of transistor M2. I apologize if my handwriting is getting crappy. And not, did you just, where is R3? M3. Oh, okay. So that's fair. So how do I know whether or not that transistor M3 is part of the feedback loop? Okay, so I'm looking at something connected between my output and my input, because that's how my feedback is connected, between the output port and the input port. So this is between, this resistor R1 is between the output port and the input port. My transistor M3 is tied to the output port, but it is not tied to the input port. So it is not part of my feedback loop. So this is a two-stage amplifier, right? So the output of stage 1, which is the voltage here at node X, feeds the input of stage 2, right? So that's just cascading two amplifiers together. Our feedback is not, so our feedback is effectively connected across both amplifiers, as opposed to having a feedback network for for amplifier 1 and a feedback network for amplifier 2, which is what we saw most of the time back in circuits 2. So what I'm saying is that we have something like this. Here's amplifier 1, here's amplifier 2. Here's K. All right. So here is R2. Here's R1. This is port 2. This is port 1. So our input loading resistance R11, again, we see that by looking into port 1 while shorting port 2. So that's R1 in parallel with R2. For Friday, I'm going to have different feedback networks for us to look at, so it's not going to be this repetitive. R22 is going to be looking into 2 with 1 open circuited, so that's going to be R1 in series with R2. And then our feedback factor K, something in chat again. Why is RL not a port of the feedback network? Because RL isn't connected to the input. It's connected to the output, but not the input, so it can't be part of the feedback network for the exact same reason that transistor M3 isn't part of the feedback network. K is R2 over R1 plus R2. All right. So our open loop circuit is going to look something like this. IS1, 2. My resistance R11 will be connected to the input port, so that's why it's going here. Here is IS3. This resistor is going to be RL in parallel with R22, just so I don't have to keep drawing resistors. But so my resistor R22 is connected between the output and ground. Here's transistor M3. And finally, here is my output. And to make our lives much, much easier, we are again going to break this guy down into two circuits. All right. So I'm going to say this is my voltage Vx, and overall we are going to have Vx over Vn representing the transfer function of the first stage, and then V out over Vx, which is the transfer function of the second stage. And we multiply those two gain stages together, giving us the overall open loop gain of our system. Everybody on board with that approach? Doing it all in one go is terrifying. I tried it multiple times. All right, so because we have a messed up differential pair, again, we can't do simple half circuit analysis, which would tell us that our output signal would just be, negative GMRD, right? GM1RD. So because we don't have a symmetrical circuit, we cannot simply use our half circuit. Another thing that we can't do is we can't say that this voltage at this node right here is 0, right? Because it's only 0 when this guy is symmetric. So we're going to have to look at our small signal model, all right? Our small signal model for our differential stage is going to look something like this. Sorry. So here is my input voltage. Here is that source resistance RS, or signal resistance RS might be a better way to put it so that we don't confuse it with a source quantity. Here is the voltage VGS1. This is going to be GM1, VGS1. So just to be clear here, this is the gate of transistor 1. This node right here is the drain of transistor 1. This node right here is the source of transistor 1. Then over here, I'm going to have GM2, VGS2. I know that my sources are connected together, so this is the source of transistor 2. This is the drain of transistor 2. Between the drain and ground of transistor 2, we're going to have that resistor RD, since VDD is a small signal ground. And actually, let me move this over to the other side. So this is D2. And here is where we take our output voltage for this stage, which is Vx. And over here, we have VGS2. Here's our resistance R11, and there's ground. So anybody have any problems with my small signal model for just the left-hand stage? Everybody okay? Everybody see anything wild or crazy? I am going to do something here that's going to help with our analysis a little bit. I'm literally just going to say that there is some voltage here at this node, Vs, with respect to ground, okay? Because we know that voltage, it could be 0, but it isn't definitively 0 because our first stage is not symmetrical. All right, so I can make a couple of quick observations here. The first of which is that my voltage VGS1 is Vn minus Vs. Anybody have a problem with that? All right. The second observation that I can make is that my voltage VGS2 is just negative Vs. Right? I know that no current can flow through my resistor R11, so the positive polarity terminal of VGS2 is at ground, whereas the negative polarity terminal of Vs is at ground, so these are just identical voltages, but with opposite polarities. All right, so if I do Kirchhoff's current law at node S, what I get is GM1 VGS1 plus GM2 VGS2 is equal to 0. And so if I substitute in my relationships for VGS1 and VGS2, I get GM1 times Vn minus Vs plus GM2 times negative Vs is equal to 0, or GM1 times Vn is equal to GM1 Vs plus GM2 Vs. And so from this guy, I can write Vs is simply Vn times GM1 divided by GM1 plus GM2. Everybody okay with this small amount of algebra? Nothing seems too wonky. All right. Using Ohm's law, if we look here, our output voltage of this stage, Vx, is simply the current flowing through RD multiplied by the resistance, RD, right? That will be Vx with respect to ground. So that's going to be negative GM2 VGS2 times RD. Which is negative GM2 times negative Vs times RD, which just looks like GM1, GM2, RD divided by GM1 plus GM2 times Vn. And from here, we can get our transfer function Vx over Vn is GM1, GM2, RD over GM1 plus GM2. So our first stage is analyzed. Everything is hunky-dory, all right? Now let's look at our second stage. This guy is something that I hope we can recognize, okay? Small signal. Our current source IS3 looks like an open circuit. So to me, this is a source follower with some sort of loading resistance, right? Which is exactly what it's supposed to be. So because we know that it's just a simple source follower, for our second stage, V out over Vx is going to be equal to GM3 times RL in parallel with R22 over 1 plus GM3 RL in parallel with R22, which gives us an open loop gain of A1 is equal to GM1 GM2 RD divided by GM1 plus GM2 multiplied by GM3 RL in parallel with R22 divided by 1 plus GM3 times RL in parallel with R22. All right, now let's go revisit things. What is my input resistance, my open loop input resistance when I look in through a terminal? RS in series with infinity, which just looks like infinity. And if we look in through here, what do we see? That is correct. So we're going to see RL in parallel with R22 when we look down. We're going to see 1 over GM3 when we look up. So R naught is 1 over GM3 in parallel with RL in parallel with R22. And then from here, we have all of the different parameters that we would need to construct our closed loop gain, our closed loop input resistance, and our closed loop output resistance. So that is the hardest problem I could find. And in my opinion, it wasn't actually all that hard. I'm sure I'm an asshole for saying it, but yeah. But I mean, so let me ask you guys a question. How did the analysis of this problem differ from the previous one? It didn't. We just split it up into 2 stages, which were easier to analyze. Right, which is the exact same thing we did in the last one, except that just stage 1 was something that we hadn't seen before. So it required actual analysis, not, oh, that's familiar, so I just know how it works, right? So again, this is the hardest thing that I could find in any of the different textbooks I had, and we knocked it out relatively easily, okay? So if this made sense to you, you're in fantastic shape for what's coming up on the test, okay? I will tell you, it's going to be way more similar to your homework problem, which was the first example that we knocked out in like 4 minutes, all right? That's enough out of me for today. So when we reconvene on Friday, we will be looking at transconductance amplifiers, both as a ideal case and then what we need to do for practical cases to modify it and be able to solve for all the different parameters. And then I'll have a couple of examples prepared for that. Monday, we will do either current amplifiers or trans resistance amplifiers. Wednesday, we'll do the opposite. Friday, we have our final. So this is taking these abstract feedback loops and all this kind of stuff and applying them to transistor circuits is literally all we're doing for the rest of this class, with lots and lots of examples, so that when your test comes, you think, geez, this was easy. That's my hope anyway.
Do you have a concern about the test?
Sure.
I've had to use MathCAD on a couple of them, and my calculator just says no.
Uh-huh.
So I don't understand the deal. But whereas when you're doing the test, my calculator may just be like, no, I can't.
All right. So like I said,
And it's funny initially for this, the last part we covered too, where the equations got so nasty, and I'm like, oh, I can plug all that in my calculator, and it just said,
I mean, for me, I always tend to store variables and all that kind of stuff to make the equations look a little bit easier. And so like when I write down things, I will explicitly write on my paper, like this is stored as A, so that I don't make mistakes like that. Yeah. Yeah.
I can plug all this in on my calculator.
Yeah, anytime you can simplify, 4 or 5 terms into a single number and store it as a variable, do that, because you're much less likely to make calculation errors on those small things than on the large things, where one misplaced parentheses will wreck everything. So that would be my best suggestion. But for the exam, I would expect something of the difficulty of examples 1 and 2, which were the same circuit, because you don't have an hour and a half to just look at this one problem, right? Yeah. I mean, so for me, like I would just say, oh, like I would store, this is one variable A, this is one variable B, so that I know that those two multiplied together is my open loop gain, right? Because that's a relatively straightforward calculation, as is the next step. If I know I'm not going to have to do too many steps, I might get lazy and store RD2 in parallel with R22 as a variable as well, because I know it pops up over and over and over again. So for the TI calculators, I think you have 8 different variables that you can store to. For the Casios, I think it might only be 6. So,
You can use X and Y.
yeah, I don't know. That would be my biggest suggestion, is get comfortable storing stuff correctly, and then literally just write, like I said, this was A and this was B, so that mentally you know what they are. No, I mean, that's literally what I do to make sure that I can solve your problems with the calculators that you're allowed to use in a timely fashion. Yeah. So like when I determine how long it takes for me to work a problem for you guys' test, I'm doing it usually on a TI-36X because I'm faster on it. So I'm not doing it in MathCAD. I'm not using any fancy calculator. I'm using the same $12 peasant calculators that you are.
I wasn't ready to put my homework. I'm like, I don't know how many times I saw like half error or stack overflow. I'm like, this is a
Yeah, no. Like when I do homework solutions and all that kind of stuff, I definitely do it on MathCAD and stuff just to keep track of things. But for the test, to make it fair, I have to make sure that you can do it on the calculator reasonably. So, yeah, no, I'm sure I'm a jerk, but I'm trying not to be a huge one. So,
and it's not just this. It seems
yeah.
like this last 2 quarters, every equation we have in my calculator is just like laughing.
Yeah.
So it's like the magnetic side too.
You're having to do the fields class on one of those shitty little calculators?
The homework I do not.
Okay.
But then luckily the test for take home, but I usually start with my calculator. And I'm like, the first time it says anything other than the answer, I'm like, no, but just.
Yeah. All right. See you guys on Friday.